Hello, this lecture is about the conservation of energy. Our objectives are to explain the law of conservation of energy in your own words, so you should be able to say what it is and maybe list off some examples. Know the difference between energy conversion and energy transfer and provide some examples of each. And you should be able to draw an energy flow diagram for a scenario involving energy conversion and transfer. So let's start with the law of conservation of energy. And this law basically says that energy cannot be created or destroyed. We talked about energy a little bit in the last lecture. We said that energy is the stored ability to cause change. And whatever this thing is, this ability, this stuff that allows us to change things, we can't ever add any more of it in the universe or get rid of any of it. We can't destroy it. So the total amount of energy in the universe remains constant. And this is an interesting statement because obviously we haven't measured the entire universe. So we actually don't know 100% if this is a true statement. But for everything that we have observed in systems that we can do very careful experiments on, everywhere we observe so far in the universe, this has been a true statement. So as far as we know, the law of conservation of energy is a true statement. And we assume it's true everywhere in the universe. So there are two things that energy can do. The first thing that it can do is be converted. And energy is converted when it changes from one form to another. So you might think about examples of that. We talked about forms of energy in the last lecture. You might give yourself a little example here. Let's say I drop a ball from a height, and that would be converting the energy it had at the very beginning, gravitational potential energy, and it would convert into kinetic energy because it's speeding up as the ball drops. This is an energy conversion when I change one form of energy into another. Other examples might be we could burn a fuel. In the last lecture we talked about fuel being chemical energy, and if we burn it, we're creating heat out of it, which means we're getting some thermal energy out of that fuel. So what we're doing is we're converting chemical energy into thermal energy. That's a conversion, one form to another. The other thing you can do with energy is transfer it. And energy is transferred when it moves from one object to another. An example might be if I'm pushing a boulder up a hill, I am using my own energy to transfer some energy to that boulder. I'm giving that boulder height. I'm giving it gravitational potential energy because it has height. That energy wasn't free. It had to come from somewhere. It came from chemical energy in my muscles and from the food that I ate. I had to give it that energy to get up to the top of the hill. So this energy doesn't come from nowhere. It has to come from somewhere, another form of energy or another object. We can show energy conversions and transfers with an energy flow diagram. And this is a diagram. It shows how energy is moving through a system, and it helps us keep track of all those conversions and transfers. I'm going to give you some steps for drawing an energy flow diagram, and then it's actually easier to see this through some examples. So I'll show you some examples which will make it a little bit clearer. So just write this down for now, and then we will see an application in just a minute. So steps for an energy flow diagram. First of all, draw the forms of energy that you know exist as boxes. Just put them as boxes on your diagram. We're going to connect those boxes that show the conversions and transfers. So we do that with arrows that we draw between the boxes. And then we can label the diagram with the objects that are doing the transfer or conversion. Now this probably doesn't make a lot of sense right now because it seems very abstract. I think it's going to be a little bit easier if we show this through an example, which we will do next. Here's an example. I have a battery over here. Inside the battery, in this particular battery, is zinc and manganese oxide. They are chemicals that store some energy in their molecular bonds. And then I have wires that are connected to a bulb. Current is flowing through that wire, electrical current. It goes to the light bulb, and from the light bulb we get light and we get heat out of this light bulb. So my task for you is pause the video and see if you can write an explanation of how energy is converted and transferred in this example. So start with the battery and end with the light and heat. Use the definitions of conversion and the definition of a transfer, energy transfer, to see if you can write this explanation. And I'll give you the answer in just a moment. Did you try it? Okay, let's see how we did. So I'm going to start a little paragraph here. Well, I know that energy is going to start in the battery in the form of chemical energy. So let me just write that down. Energy starts in the battery in the form of chemical energy. It's right over here. Now, one of the things that a battery does is it stores energy in the form of chemical energy, and then it turns it into electrical energy, which is energy that's a little bit easier to use, certainly for circuits and electronic devices. So the battery converts the chemical energy into electrical energy. And that energy doesn't stay in the battery, it's being transferred to something. It's being transferred to another object, the wire. So whenever I move from one object to another, that is a transfer, an energy transfer. So I have one conversion so far, chemical to electrical, and I have a transfer. The battery converts the chemical energy into electrical energy and transfers it to the wire. Okay? One form to another, one object to another. Conversion, transfer. Okay? The wire keeps it in the form of electrical energy, but it moves it to another object. The wire transfers energy to the light bulb. So that's one more transfer because I'm going from one object, the wire, to a new object, the bulb. And that's an energy transfer. Now the bulb is going to take that electrical energy, because that's what my energy is in the form of right now, electrical energy. It's going to go through this thing called a filament. We'll learn about that later. And it's going to convert that energy into other forms. And one form is light. And if you remember from the last lecture, light is a form of radiant energy. So the light bulb converts the electrical energy into radiant energy, which is the light, and something else. If you touch a light bulb, it's going to be hot, especially these old incandescent style light bulbs. They use up a lot of energy as heat. And that heat, as we learned about in the last lecture, is thermal energy. Thermal energy, or heat. So here we have kind of a story from one end to the other of what happens to this energy. It starts inside the battery as chemical energy, converts to electrical energy, transfers to the wire, transfers to the light bulb, which then converts the electrical energy into radiant energy and thermal energy. So this energy right here, the light and the heat, it wasn't free. We didn't just make it out of thin air. It had to come from somewhere. It came from the electrical energy that was in the wire, and that energy came from the chemical energy that was in the battery. We could keep backing up. How did the battery get its chemical energy, and so on and so forth, all the way back. But there is no new energy there in the entire universe. We're just converting it from one form to another, or transferring it from one object to another. That's what conservation of energy means. Okay? All we can do with energy is convert it or transfer it. It doesn't go anywhere. Now, how am I going to draw an energy flow diagram for this example. Let's go back to my rules. Step 1, I'm going to draw forms of energy as boxes. And then step 2, I'm going to connect them with arrows to show all the conversions and transfers. And step 3, I'm going to label that diagram. So let's see if we can do that for this example. We already wrote out for ourselves what happens in this scenario, so we can use that in making our energy flow diagram. I know that energy starts in the battery in the form of chemical energy. So let me just draw that box. I'm going to label it chemical energy. Now that chemical energy gets converted to another form of energy, which is electrical energy. There's my box for electrical energy. And I think about what is the object that is doing that? What physical object is that happening in? It's the battery. So I just label this arrow with the battery. Okay, and the battery is taking some chemical energy, turning it into electrical energy. That electrical energy is going to flow through some wires. And it ends up in the light bulb, which is going to convert it into two other forms of energy. If I want, I could repeat my little electrical energy here, just so I'm bookkeeping it. So here's electrical, and that happened through the wires. And that electrical energy, we turn it into light and heat in the light bulb. So I'm going to draw two more boxes to show my two more forms of energy that I have. Radiant energy and thermal energy. So those are my arrows showing that energy was converted. And what does that is the bulb. Okay, pretty straightforward to draw an energy flow diagram. Once I know the story of the energy, once I've analyzed my system and come up with the story, how does energy move, what forms is it in, how does it convert and transfer, putting it into visual form like this in an energy flow diagram is pretty straightforward. Okay, let's try a new example. Now this is a hydroelectric dam. It's used to generate electricity for cities and people to use. And the way it works is this. We dam up a river, so we're forcing water in that river to get up to a very high point up here. We're building up the height of the river. So a lot of height in the water. And then we allow the water to fall through this narrow passage. So it falls from a height, and as it falls, it turns this turbine. So there's motion here in the turbine, and the turning turbine is going to move some magnets around, which we'll talk about later, and that this generates electricity. We're taking this motion of the turbine and making electricity from it, and then sending it out on transmission lines out to the cities. So same task. Can you write a paragraph description of how energy is converted and transferred in this scenario? And once you've written that, draw an energy flow diagram for this scenario. So pause the video and try that out. Okay, let's see how we did in writing our story of energy. I know that energy starts in the form of gravitational potential energy, or GPE, because it is stored in high up water. Remember that height gives this water gravitational potential energy. Now, as this water falls down through this passageway, we're converting some of that GPE into KE, into kinetic energy. We're changing it into kinetic energy of motion. So the GPE converts into kinetic energy, KE, as it falls, turning the turbine. Okay, now the turbine is moving. So here's the kinetic energy. It's right over here. We moved it from up here to here. Energy's hanging out right here. So that motion of the turbine is now turning the generator. Okay. The turbine turns the generator, which converts the kinetic energy into electrical energy. The energy is then transferred to the power lines, which transfer the energy as electricity to the city. Okay, you don't have to have it written down exactly this same way, but if you have all the the same transfers and conversions, then you've got the right idea. Every time energy moves from one object to another, let's say the water to the turbine, that is a transfer, energy transfer. Every time energy changes form, that is a conversion. So you see the water, it has energy up here. As it flows down, the energy is still in the water, so it didn't go to a different object, but it did change form. It changed from gravitational potential energy of the height into kinetic energy of motion of the water. Okay, so that's the story of energy in this case. Now, how would we draw an energy flow diagram for this scenario? I know that energy starts in the form of GPE up high in the dam. So here's my GPE, and as it falls, I know that it turns into kinetic energy. So let's draw that. How about KE for kinetic energy? And that's happening as the water falls. So water's falling down the dam, down this little chute there. They're calling it a penstock, and it converts to kinetic energy. So now that kinetic energy, it stays in the form of kinetic energy when we move it to the turbine. It transfers to the turbine. Okay, so we have kinetic energy is moving through this turbine, staying in the form of KE. And the generator is converting that kinetic energy into electrical energy. So I have one more step here. Electrical energy with an arrow. And what is the device that's doing it? It's the generator. Okay, so this gives me a nice little flow, and you can see that the energy is starting off in the form of gravitational potential energy. Water falls, turns it into kinetic energy. There's a conversion there. Transfers to the turbine, still in the form of kinetic energy, and then the generator is going to convert that into electrical energy. Okay, so we have all these steps of conversion and transfer. I think you're ready for a challenge. This is under the hood of an Aston Martin. And you can see up here there's a couple of things that go in. One is gasoline. And I've used octane here. to represent gasoline, C8H18. It's a molecule, a very large molecule. Oxygen is coming in. The engine is sucking in air from the outside. Those two chemicals, those molecules, are going to be combined in combustion. We're going to burn them. And when we burn them, several things happen. First thing that happens is we get a lot of heat from that burning, from the combustion and from the friction. That heat goes out to the air. Another thing that happens is when the engine turns, it turns an alternator, which is a little bit like a generator, and it takes some of that energy and sends it to the battery and the electronics. That's how those things run. And the main thing, of course, that we want out of a car is for it to move. So some of this energy that came out of the fuel goes to the drive shaft and turns the wheels of the car. Now, this is a really complicated example. This is a challenge. If you can write out an explanation of how energy moves through this system, through conversions and transfers, and then draw an energy flow diagram for this scenario, you're pretty good on what you need to know for the conservation of energy. I'm not going to post the answer here. You'll have to wait for class. But give this a shot, and we'll take a look at it tomorrow. So let's go back to our objectives. Can you explain the law of conservation of energy in your own words? If somebody asked you, what is it? What is this law? What does it mean? Would you be able to respond? Take a look at your notes and see if you can do that. Do you know the difference between an energy conversion and an energy transfer? And can you provide an example of each one? And can you draw an energy flow diagram for a scenario that involves energy conversion and transfer? Okay? Look back over the examples that we did and the definitions of these terms to see how they get applied in real problems. See you tomorrow.